a lot of time. You want to spend your time on something valuable. And so that's what I've been doing with my partner, Chris Dombrowski, who's up in Livermore. And we started a company called Condor Calibration Services. I'm not going to talk a lot about that, except think hard before you start a startup. It's a lot of work, very rewarding. There's a whole bunch of seminars you could do just on that topic. But I'm going to talk about methane. And, we're in Santa Barbara, so methane is a topic. People think right away global warming, and that's accurate. I'll talk about that a little bit. But also the economics of losing methane. Fugitive methane is actually a big deal. We're losing a lot of energy that we'd be capturing. And also safety. Well, I'll talk a little bit about EPA and PHMSA, the pipeline hazard administration. But safety is still a big deal, and that happened. And we might remember up in San Francisco when the pipeline exploded. That was a methane explosion. And maybe or maybe not it could have been prevented, but monitoring pipelines through communities is a big, big deal. And monitoring releases out of wells is a big deal. And what you can say,
and landfills,
and we'll get to that.
and landfills,
And land. What you say about methane is it's odorless and colorless, and the only reason you smell natural gas at your house is they put something in it so you'll smell it. So odorless and colorless, highly explosive, and a real loss of energy if you don't collect it. So there really are those three drivers. And no matter what else happening politically, safety is still going to always be a big deal. And so is the economics of letting a commodity go to waste. So there's a lot of effort and a lot of activity in the last few years to solve the problem of how we're going to find methane and how we can mitigate its loss. Everything from handhelds to satellites. And I'm going to talk a little about all that. So then I'm going to go pretty fast, but I'm going to try to be as clear as possible. If you have a really high-tech question, wait till the end, because I'm going to stay as long as people want to talk. But if it's something that's not clear, just jump in and say, look, that's not clear. My wife also reminded me that after being a public speaker for all this time, I still slur my words. So I'll do my best. You reminded me that at 10 o'clock last night. Thank you. So here's kind of a rough agenda we're going to talk about. Also, I'm supposed to use the mouse. People on the Zoom can't see what I'm talking about, but when I start being Italian here. But I'm going to talk a little bit about fugitive methane. I'm going to talk about what the government's recent investment over the last 4 years was, some definitions, some remote sensing solutions in general, a little bit about the spectroscopy of methane. What does methane look like or what it does not look like when you try to see it? Remote sensing techniques, some example imagery, which is really fun. And then what challenges really people are going to face when they build systems to detect methane. And I'm going to talk a little bit about what Condor does at the very end, which is we're trying to bring everybody together under common targets that allow people to look at it with their system. And then someone looks at it with a completely different physics. Can they agree on the answer? Well, they're going to agree if they have a common target. So that's what Condor is really about. It's building those common targets. I think everybody here probably has seen all these words, but I'm just going to quickly say, I'll say pixel a lot. And pixel is the size of the individual detector element, but I'm going to talk about projected pixels or the ground sampling distance, which is if you have a sensor and you're far, far away and you project it back onto the ground, the pixels of a satellite might be 30 meters across, while the pixel of a handheld camera may be centimeters across. So it's very important to sensitivity is how big the pixel is. Hyperspectral, many people know what that is, but for our use here, it just means many, many spectral bands. A hyperspectral camera may have 256 bands in it or 256 colors in the detector. Short wave infrared, we're going to call here between 1 and 2.5 microns. Long wave, 7.5 to 13.5 microns. Both of them defined almost exclusively by the water absorptions that are blocking a lot of the rest of the wavelengths. LiDAR is LiDAR. And parts per million, I'm going to talk about this as parts per million and parts per million volume, which basically means if I have a bottle of gas and it's 100% methane, it's 1 million parts per million. So if we're looking for gas concentrations in the atmosphere, we're talking 10, 20, 100, 1,000 parts per million. So very, very small amount of methane has a very, very large effect on the atmosphere. We'll talk about that real quick. So those are just some definitions. Here's the news part. Methane is a very potent greenhouse gas, 80 times more potent than CO2. And so people talk about methane in terms of how much its effect is relative to CO2 all the time. The opportunity is that methane only lasts in the atmosphere about 12 years, as opposed to CO2, which will last hundreds of years, right? So there's an opportunity to actually clean up methane. Recent studies show, and this was a very disturbing statistic when I found it, was that EPA had been underestimating methane by about 3x as far as the release rates. So rate is really important, right? How much is going up per day? EPA was probably off by about a factor of 3 up until maybe 2 years ago or a year and a half ago. Methane probably accounts for 30% of human caused global warming since the Industrial Revolution. It's a big number.
Is that reflected in that 3x adjustment?
No, this is just releasing. Yeah, no, it's not. It's not reflected in that. No. So we're talking very, very briefly about FEMSA and EPA regulations. Here's the commodity number, right? $13 billion spent on methane mitigation in 2022, and probably it'll grow to $48 billion in 2030. Those are very large numbers for people who are paying attention and saying, "Oh, I care about this, whether the regulation or not, because we're losing money." And so there's a whole bunch of different forcing functions in here. As far as as far as what are the sources, I don't know if anybody online can see this. I'm going to try to point to that. But between landfills, poop, and natural gas loss, it's about 75% of the methane load that's emitting up into the atmosphere. So what I'm calling here, because my grandson said I had to call it poop, this is industrial farming, this fermentation. So there are these sources, some of which are going to be easier than others to fix, but 75% of it is just those three. And I'm going to show you examples of imagery showing each of those three in imagery already, that they can say that pig farm or that landfill is putting out methane at about this rate. And that's where Condor is going to come in. We don't like about this rate. We want to know what the rate is. And so Condor's whole reason for being is going to be to look at how can we quantify that better.
Question on what's the mechanism that the methane that is in the atmosphere is like?
It's UV. It's being decomposed at the molecular level. It's forming. I can't tell you exactly where it goes to first, like a formaldehyde, but it's basically the upper atmosphere is just chews it up.
Okay.
It chews it up. Unlike when you hydrocarbons, fluorocarbons, they got chewed up, but then they made chlorine radicals, and boom, the ozone layer gets crushed. Right. This is just, if you can knock it down, it's just going to come out of the molecule. It does not have the same greenhouse forcing function.
And so the 12 years process, is that basically that's how long it takes for the methane to elevate?
No, it's kind of like a decomposition rate. It's kind of like 1/E for decomposition.
Okay.
So you put this methane molecule in the air, statistically it's about 12 years for its half-life.
Okay.
Yeah, and it's half-life. But still the tail goes, right? And so there's been a substantial investment to try to curb emissions during the Biden administration. It's clear about that. That's what that was. And we all saw the Inflation Reduction Act. $1.36 billion was put out there. Not in R&D, that's the second part. Going out there and funding people to start cleaning up what was leaks, basically. But in that part, DOE released $850 million for methane mitigation funds, and that was for tribes, small towns, businesses. We're on one of these grants to develop technology and develop process and practice for how to clean up methane locally. So that's a big deal, right? This is not some big government thing. This was right down to individual people could ask for funds and learn how they were going to control methane releases on their properties where there was oil and gas production being done. EPA drafted new rules on methane, carried a stick approach. It was lost revenue tax, not a fine. But those rules are being rewritten as we speak, and we're just going to have to see how that all plays out. So, that's sensitive. Back. Let me go back. I'm frozen. Okay, there we go. So this slide really has one thing I really want to say to this audience more than anything else is the leader played a role here, a really important role, because I'm going to show you where these methane detections occur spectroscopically, where they are colored. Mercatel, InGas, silicon bib, all these detectors here. So these kind of organizations, DOE, DOD, OGAs, funded work on these focal planes and these kind of technologies and the rogue back ends and all that work. You probably know someone who worked in this field that led to this point. And we can make the same conversations about the laser development here that started UCSB, has become a company here. Some of those folks are here today. It's a hotbed for this kind of work, and you should be proud of that. The other thing I'll say here is that in 2023, we were still seeing a lot of initiation of government-sponsored programs to organize people together, all of government approach on methane. And Condor was on one of these committees. A very significant fact, there's some encouragement here. In 2024, the Environmental Defense Fund deployed their own $250 million satellite called Methane Sat. I'm going to show you some of that data. Extraordinary. A nonprofit did that, put a satellite up in space where they could look down and do a whole of world look at where the big super emitters were. I'll show you some of that data. And then we formed at just about the same time in 24. So here's just three different vehicles, if you will, 3 different pixel sizes, 3 different types of technology. I'm going to talk about all these a little bit, but UAV platforms, airborne and satellites. Satellites, global coverage. Airborne, pipelines and wellheads. And UAVs, oil fields, offshore oil. How do you get to those guys? Well, this is one way you can cover those effectively. So there's a whole set of technologies being developed to go after methane. This is the slide that's going to hurt a little bit. So I'm going to try to go through this. This is what you can see in the visible. So this top of the slide here, this is all we can see in the visible. Again, I'm pointing at the slides. I apologize for people online. I get that right there. There's the mouse. Methane absorptions are shown down here in red. They're all in the SWIR and in the long wave. So you can't see methane. There's a good reason. It doesn't have transitions there, but they have transitions in this region. And thanks to all that detector development over the last 40 years, we can see those transitions. And I'm going to talk about them, a couple of them specifically in regions A, B, and C. 1652 nanometers. Some people here are interested in that wavelength. In the shortwave infrared at 2.3 microns or 2300 nanometers. And out here in the thermal, where Plumeri is working right now, they're here also. And the long wave transitions, they're here. In regards to how important it's, so I'm going to talk about these 3 regions, A, B, and C. Where primarily I'm going to speak to is that in region A, good lasers, high power, LiDAR. In region B, good detectors in the SWIR, 2.5 microns, hyperspectral. And in the long wave, single band cameras and hyperspectral systems in the long wave. Those correspond to atmospheric transmission windows, so we can get that light through the atmosphere. Not so great for other gases. Some of the gases, you simply do not have good feature space in those windows. But methane was like given to us, like, solve this one, you can do this. Okay, so I'm going to show a couple of those now.
What about that other one that's being?
So that's great. I didn't want to get into that. That's a propeller head question. This is the midwave. Really good from passive remote sensing sense you got the sun, you got thermal. It's just more complicated. We think it's a great place to go. Extinction coefficients are really high, but it's not what's being used in remote sensing routinely right now. It's a place to go, especially with the right lasers are there because the transitions are larger. But these are the three biggies of the four that are possible. I knew someone was going to catch that. So last thing I'm going to say is I'm going to show you just the spectra are fingerprints, right? So they're a fingerprint spectra. So if I have a detector that somehow magically you give me X and Y pixels, a picture, and every one of those pixels, I have a spectrum. If I can record that spectrum at every pixel, I get the opportunity to look for a fingerprint so that ultimately I can assign methane to each one of those pixels. And now you can see a false color plume. So everything I'm going to show you right now that looks like methane is all false color, right? It's all in the infrared where we can't see it. So got to keep track of that because it's easy to forget. Okay, so now some of those remote technologies I just showed A, B, and C. So here's our continuous wave absorption LiDAR at 1652-ish. And this is a Bridger photonic system. It's got a laser. It's rastering around the ground, putting a whole bunch of points out like a pointillist painting. And then they make a map for it and do a little bit of nice spatial smoothing. But this is what the Bridger system sees from a Cessna at higher altitudes. This is the map of the system. And I'll get into why that works so great in a minute.
You can't do that passively with sun.
Yes, we'll get to that. Mark,
Sorry.
Number two, passively with the sun. So this, and that's a good reason why you still want to do it with lasers. I'll get to that. But this is satellite. This is the work. This is methane sat from space. It's the bands are shortwave, so that's between 2 and 2.5 microns. Notice these are real pixels being painted, false color, big pixels. Satellite systems, big pixels. You do not have 10 million pixels operating from space. You have maybe 1 million pixels operating from space, like a sensor. So they tend to be larger because they're trying to cover so much room. Right? So even though this is a push-boom sensor, which I'll talk about, the pixels are really large. And typically, the smallest pixels we're seeing operating right now that are detecting methane are from Orbital Sidekick up in San Francisco. Those are 8 meters across. Methane sat's about 25 meter pixels, and then they go up from there. So great for super emitters, big sources, and I'll show you some data. They cannot hide a big source from the satellites. On the far right, number C is, my C disappeared, handheld thermal. So these are thermal cameras. And in particular, I'm showing FLIR, right? Santa Barbara. This is a FLIR camera output of methane with a handheld system that you can see the tech is using right there. And this is known as optical gas imaging.
I think that's their midwave system.
I don't think so. It might be.
That's cool.
It might be, yeah.
What technique does it use?
It's using a single band camera with a filter. I'll get to it. I'll show you. Single band camera with a filter. And Mary might be right. It may not be their long wave. It might be their mid wave. So this is just a little bit comparison slide here. Satellites, airborne, UAVs, and towers. Let's not forget towers. And the pixel size are shown here in the third column. They're going from 30 meters down to a fraction of a centimeter. What does that mean? That means satellite SWIR hyperspectral for methane with more than 10 kilograms per hour. That's the bottom, that's the floor for that. While the LiDAR systems from aircraft certainly is probably 100 ppm meter. Much better sensitivity because of the technique. And then you get down to the handheld optical gas imagers, and the published number there on the FLIR site. Is anybody here from FLIR? Yeah. It's about less than about 0.35 grams per hour for small concentrated plumes. I can't see that if I take a FLIR camera and I stand off 2 kilometers where my pixels are giant. I'm not going to see that number. So we have this sensitivity relationship with pixel size, and something that has to be continually looked at, because right now there is no metric. There is no way to compare them.
You've spoken about pixel size, but what about pixel depth? Like when you're satellite, you're looking through the column of the entire atmosphere.
That's right.
So,
So it's, yeah, no question, it's an effect, right? You're sitting in those spectral windows, and it's a lot of horsepower is spent on optical compensation of the atmosphere.
okay.
So that's part of the reason why they're probably at 10 kg per hour. So pixel size and some of the sensitivity. But by the time you get into an airplane, you're flying at 60,000, 50,000 feet, you got the same atmosphere, really. So it is more of a global problem than I would say specific to satellite collecting.
What's the difference? How do you translate between kilograms per hour and parts per million? Is there some kind of ratio?
You guys would make me go there, right? So this is the biggest problem. When we met with EPA over a year ago, we told them about the bags and what we were doing with our calibration. They said if you were publicly available to us a year ago, we wouldn't have wrote the regs the way we did. We were talking to the enforcement arm of EPA. The reg is written in something that we can really talk about release. So it's kilograms per hour. The part per million meter number, or any of the numbers that are coming off any of these detectors just by themselves, is really a concentration number. You have to put in a model for how much wind is there. You got to talk about dispersion. And so there's modeling, and now they've got a whole new source of errors, which is turbulence, wind speed. You cannot go take a wind speed from the airport. So you need to have a technique, or maybe someone invents a technique where you can take the imagery themselves in motion and derive the wind speed. Now you can connect all those together. Without that, there's this little needle that isn't talked about.
So you prefer the kilograms per hour metric?
I don't prefer it. It's what's written in the regulations.
Okay.
So if you're running a facility, you don't necessarily care instantaneously what I saw. You have a rate that you need to fix. And depending on the day, what people see is going to look very, very different. A day with no wind, you look really bad. So you really want to be in release rates, not what someone sees instantaneously.
They specified it at, I think at 1 meter per second when they did the specs.
Yeah. That's the kind of number, Mary, you got to be more public about.
Repeat the question, please, for those of us.
Yeah, go ahead.
old ears on this side.
I don't think Mary's just making a comment about that.
Just making a comment.
That
Yeah, but I don't care. I can't hear you.
Okay,
That means
so I'm
no
just-
one online can hear you.
Okay, so the regulation, I believe, is specified when they put the kilograms per hour requirement or grams per hour. It's specified at a wind speed of about 1 meter per second. So they actually spec the wind speed so that you can actually backtrack to the ppm approximately.
but you're right.
But I'm saying, this is being,
So to go back to your question, someone has to make a reg, someone has to enforce it. You're the guy in the ground, you're feeling the pain, it's your facility. Kilograms per hour is the way to work. Because it ain't grams per hour coming off your facility. It's a big number. So that's kind of what they settled on, and we'll see what they do as technology advances. I'm going to go through some technologies really quickly, and I'm going to come back to the LiDAR one afterwards. But in the SWIR, now we're back at A, right? We're back at about 1.5, 1.6 microns. There's some very nice sharp lines that have very low atmospheric interferences from water. And so that you saw that hashtag, or that fingerprint I said earlier about what the fingerprint looks like. I'm just picking out one of those lines, a very, very sharp line here on the screen. And if I take a laser system and I modulate it across that line, and I look at the scattered return back from that laser, I can lock in on that signal with a lock-in amplifier. And if I do some other games, I can both lock in on the signal and I can lock in on the frequency that I'm scanning across. I can get directly to ppm meters. And so this is a very powerful, viable technique called tunable diode laser spectroscopy. I've got nice slides for this. I'm not going to show them. It'll take too long to explain them. But basically, laser goes down through the clouds, scatters off the ground, comes back up to the aircraft, which is their primary sensor du jour platform. And right here, is a picture of bridge or system sitting on the strut of a Cessna. That means anybody can fly this. So we can see broad applicability for that laser system. We're not talking about a very large system in the belly of an aircraft. You can do this from airborne platforms, from something as simple as a Cessna. And that's one of their data products from. I'm not going to, I'll talk about this later if anybody's interested. Very elegant light modulation technique. We can talk about that later, perhaps. Mary's right. This might be a FLIR image from the midwave, but basically what's going on here on an OGI camera, there's a cooled Mercatel detector or other detectors that are sensitive to the wavelength you're after. There's a filter that's narrowing down into the cluster of lines, and you're doing a single wavelength image. And that's kind of what these products look like. So you're up close and personal. Someone's told you that there's a leak at that facility. This is going to get you to the valve itself. You have a handheld, low operator overhead. You can have technicians do that. This is something from some of our folks here, are also a transfer out of the DOE. They've got their own small company, Plumeria. And what they've developed is the ability to work with uncooled cameras, much lower price, and a visualization using hypertemporal imaging, where they can enhance these images from what you would see with a thermal camera without the enhancement. So that's a nice big advance also, is to get into the temporal space. Okay, so that's a little plug there for Mary and Mark who are here. Now I'm going to get to a little bit of head hurt slide, my last head hurt slide. I'm going to talk a little bit about push broom hyperspectral systems. So what I've shown here is that I'm flying over the ground, and I've got a camera that looks through a slit. So I only see these pixels that I've got drawn here, right here. Really hard to point to those with this mouse. So that's the x-axis. So those are pixels that I'm collecting over and over again. Collect as I march the plane forward. That set of pixels is dispersed on a spectrometer up onto a focal plane, which is shown here as color, a rainbow. So what you have there is you have the X pixels, you have the color, and Y is moving the camera forward, every picture forward. So what you end up getting is you end up painting what we call a push broom. And so that data shown up here in the upper right that's just showing a plane flying, and maybe you capture 100 frames or you capture 1,000 frames, but you ultimately end up what's here in the bottom right corner, which is the data cube. X and Y, and what we're showing is Z back into the page is that spectrum that I need to make the ID. So this is a hyperspectral cube. At any one pixel, I can interrogate it with software and say, is there methane there? Is that complex spectra buried in the return, the light, the radiance return? And so that's hyperspectral imaging. That's what we talk when we say we're doing it. That's what we talk about. Every one of these pixels, and I'm shown here now on the left, is a rainbow of colors, and buried in that rainbow is the spectra of methane.
John, back on the previous one with the LiDAR, and they showed the product of it.
Yes.
How is that an overlay? Like, how did they?
Yeah. What they do is they run a context camera because they don't have any image.
Yeah.
They
Okay.
run a context camera, and they have a rastering spot that's just speckling photons all over the ground in an array. And of course, they know where that array is because they're pointing it. Right. So they take all those dots and point those tainting, and they smear them all together into a model, and that's what that picture was showing. I should have said that. Thanks, Mark. Yeah, they're not imaging. They're doing a single pixel raster. Thank you. In this case, you're push brooming and you're developing a cube. And what's shown right here on the right now is our targets. And it's really hard to see. I apologize, but there's a truck here in the middle of these pictures. And there's a target sitting on top of that truck in the bed. It's really kind of hard to see, and I apologize for that. In the bottom image, that bluish green is a false color of the methane that it sees using an airborne hyperspectral system by a company called HiSpecs. And so, hello. That's the methane there, here showing in the truck bed. And you should, if you stared at this for a long time and we had hours, you would ask me, John, why is there blue outside of the target? You said the target was contained, the methane was contained, because the imprinting of the methane signature is in the light that's gone through the target, is now reflecting off the ground. So that speaks to the sensitivity here a little bit, is that we're seeing the methane feature in the light that's gone through the target and is reflecting off of other things. So that's a nice clear image. Like, yeah, that is what we're looking for. Okay, let's get on this couple pretty pictures. So this is the Tanager satellite. It's a great story here. I'm not going to get into it, but people funded this, right? This was funded to do this. They threw it up into space, which is trivializing an enormous amount of work. Within, I think it was hours of the satellite flying over Karachi, Pakistan, they had a hit. 1,200 kilograms per hour. That's the first shot at opening up the aperture. Before this, you knew you had methane because you had fire or you had a burn tower burning it off. And so all of a sudden, the whole world's getting painted with a system that can see where all the methane is being released that are super emitters. High concentrations, right? We're not getting to the small ones. Not small spatial resolution. I can't tell Larry's from Frank's if they've got facilities across the street from each other. But boy, did that get you into the neighborhood. Okay. Real exciting stuff. Get us there. Next one. Here's another great thing about this. You, as a citizen of the world, can go to carbonmapper.org and do what I just did, which is bring up the data yourself. You can go and look at any place on the planet and say, I want to know where all the releases are that are over 1,000 kilograms per hour. I want to know where all the releases are in California. How about I want to know where the releases are in Santa Barbara? Okay, you can do that. You can tell it like that part. So here's Carbon Mapper and the Planet Lab system mapping California. This is in 2016. This is when it was still an airborne exercise. It had not become satellite. And this is a platform that some people may know of. It's called Avarice. This is Avarice NG for Next Generation, flown by JPL. They flew all potential sources of methane for the state of California. They flew over the oil. They flew over the farmland. They flew over the landfills. They flew it all. Again, no hiding from an airborne platform that's sensing like this. And so what we have here is this is still from the Tanager satellite. So this is still the satellite data. Oil and gas facilities on the far left, in the middle, a landfill, and on the far right is agriculture. So nowhere to hide from the satellites if the plume is large enough. But I got ahead of myself a little bit here. They did fly it first in 2016 airborne, which means those pixels are smaller, which means their sensitivity is better. They have better spatial separation, but you just can't count on just flying. The economics of it are tricky. You really want to find your big sources first with satellites, then do what's called footprint reduction, move down to higher resolution. That's what we're showing here. This is Carbon Mapper. It's called Carbon Mapper, but really it's the airborne system. Pitus Point, great little surf break here. Up the hill on top of the mountain. Oops. Methane coming out of one of the oil and gas refineries, facilities. And this is to be expected. You know, this isn't going to be a problem that we're going to plug all these leaks overnight. This is infrastructure that needs to be changed. That's what that earlier when I mentioned that EPA money, that's to convert the infrastructure that exists. The infrastructure that exists leaks. Compressor stations leak. Transfer stations leak. Pipelines leak. But this is a really great way to say, hey, look, you have a problem here. You should probably clean this up. Let's do another one. Oops. The Hegas dump, blown in 2016. Methane coming out of the burial pile. Landfills leak methane. You can cap them. You can capture it. You have to have political will. Not going to be political in this talk, but that's all captured methane. And we're seeing that more and more, that landfills are being capped with geotarps, and they're capturing that methane and they're burning it, and they're using it for fuel. Also in this case, that's spatially getting small enough that you can almost really say, yeah, it's got to be right there. It's right there on the map. We can go right to that place and look for it. Third example, Tulare, airborne HSI campaign, again, 2016. In this case, we can really resolve these two spots. Those are probably two different farms. This is, I believe this is
Very, I'm sure.
beef. I don't think this is pork, but these are waste methane generators. Could they be captured? Absolutely. And at this kind of resolution, you can really resolve which ones are which. And there are estimates of 63 and 43 kilograms per hour. That's still a big number per farm. And what I didn't tell you earlier on, I should have, we want to be able to look at pipelines, 3 million miles of pipelines in the United States. We want to look at wellheads, 720,000 wellheads in the United States. Do you think they're leaking? Yeah. Yeah. On mass, we're talking big numbers. Singularly, maybe not so bad. Maybe 1 out of every 100 leaks. That's only 70,000 leaking wellheads. It's 1 out of every 10.
Curious, what's the complexity and the accuracy of like the image detection system?
And so what you do is you form a company called Condor and you go after that. Every one of these techniques has its own error analysis and error sources, right? Hyperspectral was really built as a detection technology, not a quantification technology. Very, very few people are using passive hyperspectral techniques to quantify what they're seeing. They have a sensor that can detect anything in the spectral regime. So they're more about it's methane, no, it's propane, no, it's dimethyl methyl def, right? They're interested in knowing what it is more than exactly how much. And so quantification and the error bars associated with that are going to be different for every technology. But certainly wind, you need to know the wind speed really well if you want to know what the release rate is. And if you want to know, quantify what you're seeing passively, you really have to have a well-calibrated sensor, not a lab calibration, but a calibration, I mentioned it, but a calibration that really takes into account the air column. What is the air column you're going through? How much is that impacting your sensitivity? So those are really, this is a nascent use for hyperspectral in particular. So it is an open question about how accurate it's going to be. But they put error bars on this. They said, yeah, 53 plus or minus 26. I'm not really happy with that as far as an error bar, right? But that's what you got. It's not 1200, right? It's a reasonable error bar.
Are the spectra then a series of photometers or is it a spectrometer?
In the case of this, it is just exactly what I showed you as far as a push broom spectrometer.
Okay, but it's not like, an RGB or something. It's not 3 different photometers.
No.
It's
This
actually
is
scanning a whole
this.
spectrum.
The average system that shot this is a push broom spectrometer. It's an unbelievable instrument with about tens of millions of dollars. It's got over 200 spectral bands in the visible and shortwave. And they take those shortwave bands in particular and they run a match filter on it and say, okay, is there methane in it? Yeah, that's a great question. Thank you.
Do you know if they look, just to follow up, if they look for SF6 with the same?
So SF6 doesn't work in the SWIR. It's a long way if hyperspectral detect.
Oh, what was the one you just
These are
showed?
all SWIR.
Oh,
Yeah, this is VMIR SWIR. I should have said that somewhere. Yeah, this is the carbon mapper, satellite system, and the airborne are only VMIR SWIR. So where they're more focused on is how's the vegetation doing, right? That instrument has enormous applicability over many use cases. Methane is just one of them.
Where's that one on the left at the bottom? It looks like it's just following the contour. Yeah, right there.
Yeah, so I wasn't gonna. So is it though, or is it the background? The background changed enough that it's not seeing the methane over the vegetation. Great question. Great observation. What the dead giveaway is why is it on the road and not in the field? Remember, this is not This is a match filter false color display of what they detected pixel by pixel, right? Individual pixels. Detecting on this pixel does not affect you in these algorithms, what you see over here. So we see this a lot in passive hyperspectral. You'll go over a certain background and everything drops out. What happened? Same thing happens with laser stuff to a lesser degree. The laser is quantitative in what's in its path, but you can hit a dark spot. You can hit a bad reflector. You don't have any return anymore. Right? These are lock-in amplifier techniques. Lock-in amplifiers do not like when your signal's going like this really hard. So they all have their foibles, but they're different. And so, well, why isn't there just one technique? That's why. That's why it's not just one technique. Which one's going to be the best technique is going to depend on spatial requirements, the lighting conditions. Be-near SWIR hyperspectral, day only. Long wave, anytime. Day only, what does that mean? That means from like 10 o'clock in the morning to maybe 3. If you're lucky, that's the day. So very much these other limits. So when someone says they want to do this with a LiDAR, maybe they want to do it from space, it's 24 hours a day. That's great. Still got to paint it with a laser. That's a really great thing to be able to do because you get this wider time. My wife, I don't know how much time I've had. My wife was in the environmental business for a while, and she worked at a place down in Ventura, and they had stack monkeys, guys that would climb the stacks and do air samples. And they say they would be driving up to the facility, and they could watch them turn the process down as the car approached. No kidding. It's just business. It's not personal. But, you know, there's a certain real advantage to having multiple technologies and multiple modalities. You cover more ground, you reduce risk, but you cover more ground with real people. Okay. Okay. So the questions have shown some of the future work that has to be done, the challenges. Pixel size is going to matter. How much you're going to paint, how much resolution you're going to have spatially on the ground. Sensitivity is going to matter. The methane absorptions are different in these different wavelength regions that I showed you, which is going to be the winner. Well, how much resolution do you need and how much sensitivity do you need? If I only care about stopping 10 kilograms per hour, I don't need a super sensitive sensor, but I need area coverage. So these are going to be the trades that are going to kind of come out of this whole field as it develops. Are we going to stay passive because of economics, or is someone going to build us a high-powered laser that's affordable? Well, maybe. And calibration will matter, and that's really where Condor is fitting in. We figure that as this goes on and people start to argue, you're going to have things that break ties. In the simplest way, saying it, you've got a place, they're saying you're emitting, you're saying, nope, it was the guy next door. How do we calibrate that? How do we show that? That's going to be the next whole level of fidelity that's required. And how do we connect these techniques that are primarily global to, I need to get to the wellhead and find a leak. And that satellite's not going to help my tech, who's walking through the facility trying to find a leak off of a compressor. So, while oil and gas, I'm going to focus just on oil and gas because that's where the regs are right now. They've really embraced remote detection, and they're investing in remote detection. There really is still no independent validation for the very imagery products that are being generated. So that's what we're interested in. So that leads to false alarms. It leads to missing things. But from a collection standpoint, if I've got to go collect over that facility multiple times because I don't believe the data, that's a lot of money. That's flying airplanes or waiting for satellite time or going and sending people into the field. That's the most expensive thing. That's why we have remote sensing. So those are the kind of things we need to work on to get surety and to generate trust. And so and also we really have a lack of standards that's pan across all the technologies. So that's what we did with Condor. That's why we started Condor. And what we're doing is now we're into the tiny piece of what we're doing is we built these highly transparent vessels. We called them get bags when I was at the lab, and we're still calling them get bags, right? So these are highly transparent volumes of gas. They are, in fact, static, freestanding plumes, if you will. When we put a target in the scene and someone flies it, our data is not separate. Our data is embedded in their data, like a watermark. If you know what's in that bag, it's in their data. It's like an Easter egg. Again, it's undeniable. It's in the pixels, okay? And so if this is the bridge between chemists and chemistry and remote sensing people. Chemists and chemistry, I've got a jar. It has this much in it. I can measure it with a GC or any number of techniques. I know exactly what's there. Try to measure 1 million jars. You go to the remote sensing side, you say, well, I got these shape files. I can see the shapes. I know the shapes. How much is really there? About this much. About this much. So somewhere in the middle, we wanted to put something together that we could calibrate against. So we build these targets and we know exactly what's in them. So we've generated a chain of custody between what's really in the bag and what they're really seeing with the image under real world conditions. And that's the point of what we're doing. That's the point of what Condor is up to.
So are you calibrating the readings or are you calibrating for a specific site?
We're calibrating. What we're doing is putting a specific amount of gas in the bag that we know exactly how much gas is in there. We know the path length exactly. So we know what the sensor should see in what's called concentration path length product. We know the concentration of the path length, so we know the total absorption. They fly it. They say, well, we think it's this much gas. And then we can say, no, it's this much gas.
So you're calibrating the reading.
We're calibrating them with our calibrated source.
Okay.
Yeah, that's the point of it, right? And to be honest with you, we're ahead. Kind of ahead of the curve on this, right? We're kind of getting anticipatory so we get people to socialize using these kind of targets. Most important to me personally is that the different technologies look at the same targets. Because while the different spectral regimes are dominated by what focal plane they have and what system they're using, whether it's active or passive, the targets work with all those fields. So we can build targets that anybody can cross-calibrate across domains. That's where I think the real help is going to be the advantage and the R&D is going to end up being. So that's ours, putting targets out up at Livermore Airport. Here's some of the data. Here's the targets. Here's a plume. But this is kind of what a target looks like. It's a mock-up of a target. STL has the operational targets, and they're going out in 5 days. 2 weeks. They're going to go out, and they'll be at a facility putting targets out very, very similar to this. And aircraft are going to fly over and make measurements.
And that's calibrated. You know, it's a controlled target.
Yeah. So Ian, I'm going to talk for Ian. Sorry. Ian's got a tank of gas. He knows exactly what's in the tank of gas. He fills the target with that tank. It's going to be X percentage of methane in that tank. So we're going from the chemist happy place to the remote sensing happy place by putting that gas in that target. Knowing the geometry of the target very, very accurately, we know exactly how much light's getting absorbed because the spectrum of methane is not changing. Great question. All right, so to bring it home, in the U.S., 30 million metric tons of methane were released into the atmosphere in 2021. Not a small number, but it's dispersed across the whole country. We calculated that if you were going to do this and look at wellheads with airborne platforms, you needed 200 teams. You needed 200 flight teams to cover all the leaks.
Wow.
720,000 wellheads, 3 million miles of pipeline. It's a job, not a science project. We know that livestock, oil and gas, and landfills are 75% of our emissions. And we know, because I just showed you, that we know how to see those leaks. That's a nice number. That's a nice number. We know that methane only persists in the atmosphere for 12 years. So if we knock it down by shutting off the leaks, first you have to find them, right? Global concentration of methane will drop. It's the same problem they face with ozone, getting chlorinated hydrocarbons out. I mean, they gave Sherry Rowland the Nobel Prize for it. It's the same kind of problem. I'm going to say that the ozone problem is much harder because they damage the atmosphere with that. In this case, we just have to get the methane out and the atmosphere will clean itself.
On your bag, with the methane in it, you have, well, you mentioned A, B, and C bands. Is it transparent to all those?
Not going to get into the details of the material science of the bags. But yes, depending on which plastic you pick, you get a different transmission window, and the different technologies tend to overlap. You can do all three,
Oh, I guess that's what I was.
but I wouldn't. I would
that's
think I
fine.
would optimize.
Okay, yeah, good enough.
It's going to be rare that we have all three technologies staring at the bags at one time.
John, do you want to ask if anyone online?
Yeah, show me how to do that.
Just verbally ask if anyone online would like to ask a question.
Would anyone online?
$1, Bob.
Do they write you?
Yeah, they unmute and start.
Yeah,
talking.
just unmute yourself and go ahead and ask a question.
Hi, this is Tom Reeder. I'd like to ask a question. Historically, there's been a lot of methane emissions from off the coast of Santa Barbara here, along with oil seeps. I wonder if that's visible, if you've looked at that at all. It would seem to be reportedly in the past, it's been called the largest methane leak in California.
Oh, that's awesome.
I know
Thank you.
Benedetto or somebody put an underwater tent to try to capture that, and you could probably measure the effectiveness of if the tent was working. I don't know if the tent is still there. Or maybe you could shed some light on that.
That's a great question. Yeah, I remember when they put that tent in. So methane and oil platforms is a very I'm not gonna say unique, but particular problem to mitigate because they're out at sea, right? So you have to be able to use a remote sensing technique that's going to work in that environment, which is wet. The background's water, and then all of a sudden it's steel, and all of a sudden it's water again. There are groups of people. There's a group that we're talking with, Canadian group called Telops, very, very interested in platforms and how they're going to mitigate platforms because of the tricky optics involved and try to hit that and see those targets. You got to kind of know your background, right? In the case of the LiDAR techniques, you kind of want to hit the target. You don't want to hit the water, right? You got to hit the target to get a strong return. And so there are people building LiDARs and are getting approved to use LiDARs on UAV systems to fly over platforms. And in that case, they're going to go look for specific things that they know kind of leak, right? There's certain parts of the platform they're going to go focus on. The airborne work that we know might happen is going to be in the long wave hyperspectral. That's a company that's going after that because they just simply have a lot of experience working out on platforms. And the other trick is you can't really interrupt operations. You can't send somebody out there and have them stop. There's safety reasons for that. That's very difficult. So you really want to do it remotely, but you got to get there, right? So either you're flying on their chopper flights, which are already existing out to those. You can see those chopper flights out to the platforms, or you got to fly with a fixed wing, or you got to fly with the UAS that you bring out there. So those are not tech questions; those are business questions, and I don't think an answer has emerged yet on which they're going to do first. And everything that they do out there has to be approved, right? So no one just says, "I'm going to go do this." Without a lot of approvals and procedural work to be done.
So
the
leaks I'm referring to were supposedly natural seeps. I remember being out there diving and just seeing gas bubbling up from the ground into the air. But aside from the oil rigs.
Yeah, that's a complex gas, right? That you might want to call that natural gas. There's all kinds of stuff in there, including hydrogen sulfide. That kind of percolation leak could be seen. You could build a marine system. You're going to have you need an economic driver that someone says, I'm going to do that. Because you can find that leak. You and I could go out there on my boat and sit out there and put a gas analyzer. We're going to measure methane. But what are we going to do about it? Right? So there are people watching the gas leaks that are coming out of that. But they're probably not going to be as driven by enforcement as someone who's leaking off the facility that can do something in remediation.
Goleta gas storage field is literally a mile.
Yeah.
Right, straight line from here.
Right.
And I believe that's the largest gas storage facility, kind of north of Aliso Canyon, which had the massive leaks a handful of years ago.
That's right.
Are you monitoring that?
We're not monitoring anything, right? We're developing remote sensing technology. Monitoring that I'm sure exists at that facility, but only because I can't believe it doesn't. That's probably a really bad logic there. They'll be on the corners of that facility somewhere. There'll be methane collectors and sensors. So not necessarily remote, but photoionization detectors or other detection technologies that are going to be able to get a whiff of the gas that goes by. And you've probably seen in Goleta, we have those things for hydrogen sulfide, right? It certainly have Mount Elwood. There's towers set up with little silicon solar detectors, and they're measuring hydrogen sulfide that way. So that technology is all the non-remote stuff, and that's probably bigger than the remote part, right? Is the on-site measurement technology. Did that answer your question?
Yeah. I have a follow-on question, which is kind of, that's not your business model.
Right.
Can it's the calibration system techniques.
Right.
That is your business model, it sounds like. Can you talk a little bit about who your customers are? Is it mostly grant funded, or is it?
Well, I have a huge pitch deck on that.
Okay.
But
and where are you in your business cycle?
Well, we're pre-seed, which just means we're broke and working really hard. Okay. So we see the folks that are going to want this in a non-adversarial way are going to be NGOs like EDF. They're going to want that technology to prove things are working. So that's one sector. Sorry. That's one sector. There's the oil and gas companies themselves that don't want to get caught not knowing what's going on. People are looking at their sites. Do I believe that? I'm not a remote sensing guy. A guy flies over my facility with a plane. He's got a LiDAR on it. He says, I've got this much leaking. I'm going to call BS. Well, you can't call BS. You don't have a standard. Put a target out. If he sees your target and tells you that the target is X, and he's giving you a number that's 10 times what the target says, he needs to go get a new job. Right? So there's the oil and gas sector, there's the NGO sector, nonprofits, and then there's communities. So you're one of the things we're doing on that funds. We're going to be going out to the Indian reservations out in Utah. We're going to fly over their facilities, and there's going to be targets put out to show, hey, look, we don't see anything over all this area that's been flown before by my business partner. Is it there? And then they have a food fight when the plane lands. No, it was your sensor. No, there's nothing there. No, you picked the wrong time of day. You put a target out, you say, yeah, I see the target. End of story. There's nothing here. I see the target. The rest of the ground has no methane coming out of it. This section of ground has none of these hidden wells that they're looking for right now. So the third group is kind of like municipalities. You've got this land, this landfill that you are accountable. Your pain level is you're responsible that you're not letting your community get whacked. And then you hired these guys to fly it. And they say, nope, can't see it. And a room fills up with people and says, prove it. So those are three domains. So they're not sectors, but they're use cases, if you will, just in oil and gas and landfills. Those three are really big. We'll see what they're going to do about industrial agriculture. That's going to be a big one. Not because their leak rates are so high, because they are high, but they're not blindingly high. No one's getting blown up, right? No one's dying, but there's a lot.
There's a question in the chat.
Can you provide us your email in case we want to contact you? Of course I can. And I think it's on the first slide. It's really long, but really simple. John D. Benedetto at CondorCalibrationServices.com. And our website, which is terrible, is just CondorCalibrationServices.com. It's a landing page with some information. I've got my card here. I can't stuff that through the internet. But yeah, we're here in Goleta.
Yeah, I really enjoyed your talk. Thank you. Is there any chance that we can have a copy of the slides? Is that too much to ask?
Talks are online.
Okay.
And
If that's okay with you?
I need you to cut off all the slides after end before you post it.
yeah, well,
Okay,
There's half a pitch deck back there that's just not appropriate to be.
well, I'll always see what you provided to us.
Right.
I'll provide you the cut copy that has it, stop it.
yes, yes.
Because we just recorded what you provided, so
Oh, yeah,
that's all I'll have to be able to put up.
Okay.
If that's
I'll
okay.
get your hard copy.
Okay.
There'll be a copy of it, because your slide isn't up there.
On our website, the former talks where the speaker has agreed, and I thought John had already gone through this, I apologize, my fault for not asking him. They're all online on our website.
Okay.
Yeah, we've skipped ours. We know ours are no IP. We're good.
But there's a difference between having a link to the recording and having a link to download the presentation.
Correct.
Do you have both?
No, I just have the recording to put up on YouTube.
But you can always contact me and I'll get you some version of that, what's up there.
That sounds good. Thank you.
The good stuff's not in those slides, right? The good stuff is conversation, we can, we'll talk to them.
Mhm.
I'd like to, eventually someday get paid. Make money. Right now. Oh, so this commentary. So you retire. Are we still recording?
I can stop the recording.
Thank you. So you retire and you tell your family that you're retired.